Tornadoes. You've seen the footage, right? Just these incredibly violent, powerful storms. But behind all that raw power, there's a really fascinating story. A story of wild atmospheric physics, a super surprising way of measuring them, and some science that could absolutely save your life. Okay, so let's just dive right in with the big question. When you hear on the news that a tornado was an EF4, with winds hitting, say, 170 miles per hour, how in the world do they know that? How do you clock something like that? Well, the answer is probably not what you're thinking. And to really get it, we have to go way up, to the birthplace of the most powerful twisters on the planet. So yeah, our story actually starts high above the ground. It begins inside a very special, very powerful kind of thunderstorm. The engine that cranks out the most destructive tornadoes on Earth. Now, this is not your average storm. This is a supercell. And the key phrase you really got to latch onto here is persistently rotating updraft. See, other storms might get a little spin here and there, but a supercell is defined by this massive spinning core. It's called a mesocyclone. And that constant, powerful rotation, that's the secret sauce. It's the source of all its incredible, destructive power.
So you might be wondering, how does a giant storm even start to spin like that? Well, it all kicks off with something called wind shear. Just picture this. Winds at different heights are blowing at different speeds or even in different directions. This creates an invisible tube of spinning air, just rolling horizontally in the atmosphere. But here's where the magic happens. A super powerful updraft inside the storm shoots up from below, and it slams into that rolling tube of air, lifting it and tilting it completely upright. And just like that, bam, the storm has its engine, a massive spinning mesocyclone.
Okay, so now we've got this gigantic, rotating storm up in the clouds, but that's not a tornado. Not yet. So how do we get from that huge, relatively slow spin to the tight, crazy fast vortex we all recognize as a tornado? I mean, the scale here is just mind-boggling. That mesocyclone we just talked about can be up to 6 miles wide. Think about that. For a tornado to actually be born, all of that incredible rotating energy has to get focused, concentrated, and funneled all the way down to a single point on the ground. This is the absolute best way to picture it. It's a physics principle called the conservation of angular momentum. It's exactly what you see when an ice skater is spinning. They pull their arms in and they start spinning way, way faster, right? It's the same thing here. As that wide rotation of the mesocyclone gets pulled inward and stretched down toward the ground, it has no choice. It has to spin faster, dramatically faster. And that tightening is what creates the terrifying wind speeds of a tornado. Now, once it forms, a tornado goes through a pretty distinct life cycle. It starts in the developing stage, maybe just a funnel cloud with some dust getting kicked up on the ground. Then it hits its mature stage. This is usually when it's at its most powerful, its most destructive. And finally, it enters the dissipating stage, where it gets all thin and stretched out. People call it the rope stage. But hey, don't let that fool you. Even a tornado that looks like it's falling apart can still be incredibly dangerous. Which, you guessed it, brings us right back to our original question. Now that we know how a twister is born and how it dies, how do we actually measure its strength? This is where one of the biggest myths about tornadoes lives. That's right. The surprising, kind of shocking answer is, we don't. We don't directly measure a tornado's wind speed. With all of our amazing technology, it's just too hard and way too dangerous to get a sensor right into the middle of a twister. So that 170 mile per hour number you hear about, it's not a direct measurement at all. It's actually a highly educated estimate made after the fact. So here's the crucial thing to understand. We rate tornadoes by the ruin they leave behind. The original Fujita scale, or F scale, was always based on damage. The enhanced Fujita, or EF scale that we use today, is just a more scientific, more refined version of that same idea. You can think of it like a forensic tool that meteorologists use after the storm has already passed. And here's a look at how that scale breaks down. Surveyors go out and they look at the damage path. Based on what they see, they assign a rating. It starts at EF0 for light damage, maybe some broken tree branches, and it goes all the way up to an EF5 for just incredible, unbelievable destruction, which they then connect to estimated wind speeds of over 200 miles per hour. But how do they make these estimates so specific? I mean, this is far from just a wild guess. Surveyors use this incredibly detailed system that's based on 28 different damage indicators. We're talking everything from different types of trees to mobile homes to schools to big shopping malls. They don't just see a broken house. They look at the degree of damage. Did the roof just lose a few shingles or was it ripped off completely? Was the whole house just shifted or was it wiped clean off its foundation?
Every single detail tells a part of the story and helps them pinpoint a more precise wind speed.
So we've gone through the science, we've gone through the measurement, but why does any of this really matter to you? Because when it comes to a tornado, knowing the reality and not the myths is absolutely crucial for staying safe. All right, let's talk about a big one. You've probably seen this in movies or some viral video. A tornado's coming and people run to hide under a highway overpass. Seems logical, right? But is it actually safe? No, absolutely not. In fact, it's one of the most dangerous places you could be. See, an overpass acts like a wind tunnel. It actually squeezes the air and makes the wind accelerate, turning tiny bits of debris into deadly missiles. You are far, far safer lying flat in a low-lying ditch. Okay, here is an old myth that I'm sure many of us heard growing up. If a tornado is on its way, you should run around and open all the windows in your house to equalize the pressure. Sound familiar? Yeah, that is totally wrong. It is a complete waste of precious, life-saving seconds. It is the violent wind and the flying debris that destroy a house, not some pressure difference. Opening windows does absolutely nothing to help. In fact, you're just inviting those destructive winds right inside. That time is so much better spent getting to your safe spot. And finally, what about that old advice that you should hide in a specific corner of your house, usually the southwest corner? Does that one hold up to science? No. The tornado's path is way too unpredictable for that. One corner of the basement isn't any safer than another. The real rule is much simpler and way more effective. Get to the lowest floor and put as many walls as you can between you and the outside. The perfect spot is a small interior room with no windows. Think of a bathroom, a closet, or obviously a storm cellar if you have one. Okay, so let's boil this all down. What are your big takeaways? First, the most violent tornadoes come from those giant spinning thunderstorms we call supercells. Second, we rate a tornado's strength not by clocking its wind speed directly, but by analyzing the damage it leaves behind. And third, and this is the most important one, your safety comes down to knowing the facts, not the myths. Get to the lowest floor, get to an interior room, and get away from windows. And that leaves us with one final thought to chew on. We have gotten incredibly good at understanding the destruction a tornado caused yesterday. So, the next great challenge is this. How do we use all our new technology, advanced radar, AI, to get way better at predicting exactly where a tornado is going to be in the next few minutes? That's where the science is heading, and that is where countless lives are going to be saved in the future.